So we look at the combined footing. So when you have two footings close by, sometimes we can go with combined footing. So again, when two columns are located close to each other, sometimes it's convenient to combine the footings to form a continuous base. The projections outside the column boundaries are selected so that the resultant load pass through the centroid of the base area when all loads are acting under service conditions. And the idea is, this is expected to give a uniform pressure under the base. And then we consider the same uniform pressure might remain under the ultimate conditions as well. So basically, we'll have a quick look at one example. So design a combined footing to support two columns located 3 meters apart. So the distance between two columns is 3 meters. The allowable bearing pressure is 200 kilonewtons per meter squared. And concrete strength is 25 megapascal and steel strength is 500 megapascal. And the size of the columns are 300 by 300 and 400 by 400. So this column carries a lesser load, 700 and 200. And this carries a permanent of 1000 and variable of 300. And so basically we have to select a suitable size for the base. So to select the size of the base, we'll simply add all these loads. And in addition to that, we'll also calculate the net bearing pressure. And I told you earlier that either we can calculate and add the weight of the base. On the other hand, we can calculate the net bearing pressure, that is 200 minus the thickness of the base multiplied by the density will give us the net bearing pressure that can be applied, which is 181.25. So the total load is about 2200. From that, you can see that we need a base of around 12.13 square meters. And this distance is 3 meters. So we can select a reasonable length for the base. So I have selected a base length of 4.6 meters. And for a 4.6 meter length, once you divide 12.13 by 4.6, you will get a width of 2.63. So I'll select a width of 2.8 meters. So I'll select a width of 2.8 meters, length of 4.6 meters. But the question is, what is the overhang that I should be getting here? What is the overhang I should be getting here? We know the total length, but we don't know what is the projection from the face of the column. To get the projection from the face of the column, we make an assumption. And that assumption is the centroid of these two loads will act somewhere here. And we'll place the base in such a way, the resultant of the soil pressure will also act through the same point. The resultant of the soil pressure will also act through the same point. The idea is, when you do this, you will end up with the same. When you do this, you will end up with no bending moment, because the resultant force is acting through the resistance. So there's no bending moment. If there's no bending moment, then the pressure distribution under the base should be almost uniform. So what we do is, first we find what is the distance to the centroid, and then we'll bring the centroid of the base to the same location. So what we do is, to find the distance to the centroid, I can take moments about column A, that is 1300 multiplied by 3 divided by the total load of 2200 kilonewtons. So that is 1300 multiplied by 3 divided by 2200 will tell the location of the centroid. So from this centroid, On either side, we should get 2.3 meters. 2.3 meters on either side. So 2.3 minus 1.77 is 0.53, and the size of the column is 300 by 300 minus 0.15 will give 0.38. And on this side, if it is 1.77 meters from here, it will be 3 minus 1.77 from the other side. That means from this side it is 1.23 meters. So we select a length of 4.3 meters, 4.6 meters. So 2.3 minus 1.23 will give us 1.07 minus 0.2, half the size of the column, will give us a projection of 0.87 meters from this side. So this will give, we get a projection of 0.87 meters from this side, a projection of only 0.38 meters from this side. Now we know that the resultant force of these will act 1.77 meters away from the center of column A, and the resultant of the soil pressure underneath also acts on the same line, and because of that reason there's no moment acting on the base, and if the moment is zero, only the axial load is there, then when the axial load is there, we can find the axial stress. So the axial stress will be given by, for design purposes, we have to go with the ultimate. So that means 700 multiplied by 1.35, 200 multiplied by 1.5. Here also 1000 multiplied by 1.35, 300 multiplied by 1.5. So you'll end up with a total load of this divided by the area of the footing will give us the maximum pressure that will be acting from below, which is 236 kilonewtons per meter square. So now the base is balanced. How we balance that is by finding the centroid of the column loads, and then coinciding the centroid of the base with the centroid of the resultant forces. So that way we can find the stress, and you know the cover to reinforcement and effective depth. I have considered an average value of 690, and we also know the punching shear, the forces in the columns, individual columns. Then we can first check whether there can be any punching shear failure at the perimeter with the selected depth of 750 millimeters. For that, we have to calculate the maximum shear strength, which is given by this particular expression. Where nu is this, so we can calculate the punchy shear resistance. But when you are calculating that, you know, VD should be less than VRD max. So what we can do is we can calculate the value 1245 kilonewtons divided by 300 into 4 is the perimeter of the column, and effective depth is 690. So we can see VD is equal to 1.5 newtons per meter squared. For column B, 1.63, and VRD max is 4.5. So generally we can have an idea. So VRD max is about 4.5 to 5 newtons per meter squared. Generally the shear strength of concrete is about 0.4 to 0.5 range. It can be more as well, but generally 0.5 to 0.5. 0.4 to 0.5 range. So that gives this indicates that there cannot be any shear failure around the perimeter. Then what we have to do is we have to find the bending moment diagram due to the loads acting on this one, because there's a width of 2.8 meters and a pressure of 236. So you can multiply 236 by 2.8, then you can find a line load. Equivalent line load is 236 into 2.8, that is 660.8. So the situation is we have a base of 4.6 meters of length and a force of 660.8, not 644. 660.8 is acting. 236 multiplied by 2.8 is 660.8 is acting upwards. So you can find the shear force here. Shear force here will be, the projection is 0.38. So the shear force at the face of the support can be found, and also we can find the shear force at the center of the support. So the shear force diagram is drawn with the center of the support. So 660.8 multiplied by 0.53 is 350. So this is the shear force at the center of the support. And at 350, we get a shear force of 1,245 kilonewtons acting downwards. So 350 minus 1,245 will give us 896. And then the shear is varying this way, because again 236 is acting upwards. So the distance between these two is 3 meters. So 896 minus 236 into 3 is 896 minus 236 into 3. Sorry, 660.8. 896 minus 660.8 into 3 is minus 1086. So the shear force goes that way. And from the shear force diagram, you can find where the shear force is 0. And when the shear force is 0, bending moment is maximum. So you know the location, you can easily find the location of the maximum moment. And considering this triangle, when you divide 896 by 660.8, you will get 1.36 meters. So you know the location of maximum moment. Because the location of maximum moment is known, you can find the bending moment at this location. So 1.36 meters from here plus 0.53. So 0.53 plus 1.36 is 1.89. So you get 660.8 multiplied by 1.39 squared divided by 2 minus 1275 multiplied by 1.36. So you get so here you get a force of 660.8 acting over a length of 1.36 plus 0.53, 1.36 plus 0.53, 1.89 multiplied by 660.8 into 1.89 divided by 2. That is the moment acting upwards, minus, you get a load of 1245 multiplied by 1.36. You get a moment of 512. I have got the answer as 644. We just have a look at the moment. The overhang is 0.53 meters. So 660.8 multiplied by 0.53 square divided by 2 is 92.8. 92.8. Yeah, that's correct. So the bending moment here will be equal to 660.8 minus, multiplied by 1.89 square divided by 2 minus 1275 multiplied by 1.36. Then minus 553. So this value may be 553, but I have considered it as 664. And similarly, on this side also you can find the bending moment. The projection is 1.07. So the bending moment here is 660.8 multiplied by 1.07 square divided by 2. 1.07 square divided by 2. 1.07 square divided by 2. 7 square divided by 2. That is 378. So this is correct. This may be slightly different, but it doesn't matter. So the bending moment, shear forces. So you can decide the reinforcement on the basis of this. And when you decide the reinforcement on the basis of this moment, you can see 0.95D governs, can find the reinforcement, and then you can find the minimum reinforcement, and you can see the minimum reinforcement is governed. Because the minimum reinforcement is governing, and when you look at the number of bars, you need 13 bars. So in this combined footing, because the minimum reinforcement is governing, we need 13 number of 16 diameter bars at the top, and also 13 number of 16 diameter bars at the bottom, this direction. So similarly, there's a projection here, and you can find the bending moment in the shorter span direction also, and then provide the reinforcement in the shorter span direction as well. And in addition to that, you can check for punchy shear failure around the most heavily loaded column. And if the punchy shear failure does not occur around the most heavily loaded column, then you will say generally the foundation is okay. So you can see the main reinforcement can be found. In addition to that, you have to check the base for shear failure. Check the base for shear failure. And you can see when you look at the shear force diagram, there's a maximum value of 1086. So the maximum direct shear might occur somewhere here, and that is D away from the face of the column. D away from the face of the column. So you have to find the shear force D away from the face of the column, and then you have to find the shear failure at the face, shear failure D away from the face of the column, and then check that as well. So here you can see check for direct shear failure, Direct shear failure is 1086 minus 286 multiplied with 2.8, and 0.69 is the effective depth, plus 0.2 is the size of the column. You can find the direct shear force, and from that you can work out what is the direct shear stress. So you can work out the direct shear stress, and you can see it's less than the V minimum value. And similarly, you can check at a distance D away from the face of the support. Here also I have checked D away from the face of the support. The reason is, here you can see when you look at the size of the column, it's only 2.8 here. And when you would say the projection from here, it is only 1.2 meters. And that means the 2D perimeter is outside the base. 2D perimeter is outside the base. So you cannot check at 2D. So instead of checking at 2D, you can check at 1D and see whether the punching shear failure can occur. But at 1D, you get the enhancement as we discussed earlier. So basically, when it comes to the combined footing, the important thing is to get the dimensions right, so that you will find that the resultant force due to the two columns will coincide with the center of the base. Will coincide with the center of the base. So because we have the repetition of calculations, I did not spend much time looking at the reinforcement calculation and so on. But only thing I wanted to highlight is the bending moment diagram. But I think this value may be 500 something, not 644. We have to just do a calculation and see. And based on that, you can work out the reinforcement. And when you work out the reinforcement, you can see the minimum reinforcement is now governing, because the reinforcement requirement here is 2421, whereas the reinforcement requirement, the minimum is 2588. So then in the transverse direction also you can check the bending moment, and I have checked the bending moment at the face of the smaller column. On the other hand, because we are having two footings, if you want, you can check the bending moment. You can consider the bending moment at the center as well. If you want, you can check the bending moment at the center as well. I have considered the bending moment at the face of the smaller column. You can check the bending moment at the center of the column as well, because we have two columns separated. And then this transverse bending, then you can check for punchy shear. And because the punchy shear perimeter is almost outside the base, I have checked at D instead of 2D. And when I check at D and consider the V reduced value, the shear is 0.281. So even without enhancement, you can see this value is less than the minimum. So the same calculation repeated, and you can see the shear carrying capacity is 0.66, whereas the punchy shear stress is 0.281. So there's no chance for shear failure, punchy shear failure. So basically the thickness selected 750 looks fairly high, and there's a chance that you might be able to reduce the thickness of the base, because direct shear is also, you can see, very low value. So any questions on the combined footing? Inudil, do you have any questions, or any other person? Sherwin, do you have any problem? Questions? Or Dean, do you have any questions? Nishan? Anybody having any questions? So if there are no questions, then we'll move to the next one, that is the strap footing. Now move to the next, strut footings. So what do you mean by a strut footing? Now combined footing, what happens is we continue the base from one base to the other and we combine that. And we also try to make sure the center of the loads acting in the two columns will coincide with the center of the base. But sometimes what happens is, we cannot fulfill that condition. In which case, we'll end up with a variable stress distribution under the base. But in such situations, there's another solution, provided the soil is fairly strong and the inner column is carrying a higher load than the outer column. So generally, inner columns will carry higher load than outer column because inner column is loaded from all directions, whereas the outer column is loaded only from one side. Because of that reason, generally the outer column will carry a lower load than the inner column. So that's one condition that you have to fulfill. The second condition that you have to fulfill is that we need to have a beam that is connecting the inner footing and the outer footing. And if you want, you can have a variable depth beam or a constant depth beam. But the important point is the beam should be cast with the footing. Beam should be cast with the footing. Then what happens is, because this column is acting eccentrically to this base, this base will try to rotate outwards. The base will try to rotate outwards. In doing so, it will induce some load on the beam. So beam will go into some hogging moment, and because of this load that is transferred onto the beam, there will be a shear force acting on this column, and due to that shear force, whatever the load that comes from here, there will be a reduction in the force in this footing. There will be some reduction in the force of this footing. Because this footing is trying to rotate outwards, there will be some increase in the force of this footing, small increase, and there will be some decrease here. And then this beam will be subjected to hogging moments, and this footing is going to rotate outwards, and that rotation is prevented by this beam. So because of that reason, the footing will need top reinforcement. The footing will need top reinforcement. Then the beam will be subjected to hogging moments, and this has to be designed in the normal way as a footing with bottom reinforcement. And even in this footing, it's a good practice to provide some nominal reinforcement at the top. And in this footing, we'll provide nominal reinforcement at the bottom. So this is how it's going to behave. So we have to select the dimensions of the bases, considering the loads acting on the columns. And in addition to that, we have to determine the bending moment and shear force diagrams for the beam connecting. And we'll make the assumption that the beam that is connecting is strong enough or stiff enough so that the rotation of this base will be almost zero. And if the rotation of the base is almost zero, the soil pressure under this base will be uniform, And here also you don't get a rotation of the base. Because of that, the soil pressure under this footing is also uniform. So we get a behavior which is reasonable. But you can see this will work well only in the case of a soil that is of reasonable strength. And if you have a clay soil that can undergo settlements, this might not work very well. Whereas if you have some lateritic soil with or sandy soils which are strong and which will not undergo settlement, differential or long-term settlements, then this type of solution can work. So can you understand how this works? It's good if you can give some feedback. So the base sizes are selected. The base sizes are selected so that the bearing pressures are approximately equal and uniform under each base. The strap beam between the footing should not bear against the soil. Therefore, the ground directly under the strap beam can be loosened and left without compaction. So we don't want this beam bearing against the ground underneath. So if the strap beam is affected by the vertical loads such as ground slabs, so if you are going to have a ground slab or whatever, then this footing, this beam can be designed to carry the load of that ground slab as well. The reason is when you are constructing the building, these footings will be loaded gradually, and in the meantime you might place the ground slab and the loads might come here before the full strength of this beam is mobilized. So because of that reason, this can be designed for whatever the sagging moments that can occur due to the weight of the ground slab that is supported by this particular beam. Or if you think that there will be some soil compaction work that can induce some loads on this beam, then it's usual to design this beam for at least 10 kilonewtons per meter. But anyway, you know, when you provide some nominal bottom reinforcement in the beam, automatically you will find that it has enough strength. Because generally, we select a beam of fairly large cross section to give adequate stiffness to assure that, you know, the rotation of this base will be as small as possible. So any question on this? Indranil, are you there?
Yes, sir. No
Yeah.
options.
Trishanta? Rupasinghe?
Yes, sir, no problem.
No problem? Right. Okay. So let's see how to do the design. So basically what we have is a situation like this. We have two forces, P1, P2. The distance between the forces is S. And then we have the reaction due to this the pressure under the base. And we consider that this pressure under the base is uniform. The pressure under this base is also uniform. That means the resultant will act at the center. So here you get a resultant upward force of R1, resultant upward force of R2. And then we have the two forces P1 and P2 acting downwards at spacing S. So the important parameter here is how much eccentricity that we like to have here. And that eccentricity will decide the size of this base, because we know the size of the column. And so when you know the size of the column, you know that this is half the column size. and the variable is extensity. So based on the value of extensity that you select, you have to size these bases. So if you select too little extensity, then what happens is you will find the width of the base has to be increased. And so because of that reason, we have to find a reasonable value for this extensity. And there's no fixed value, but you have to go for a reasonable range. So let's see what actually happens. So there are the permanent loads and live loads acting on each column. So we can, if you know the dead loads and the permanent loads and the variable loads acting on each column, we can find the values of P1 and P2. P1 will be 1.35 DL plus 1.5 live load. So P2 will be 1.35 dead load plus 1.5 live load. And the total service load will be the addition of all four loads. So then you can see the ultimate ratio is addition of these two divided by P. So we know the ratio between the ultimate soil pressure and the soil pressure. And so the ultimate pressure applied will be the allowable pressure multiplied by RU. Then, so basically we have to select the base sizes so that we will remain closer to the allowable pressure. So we have to select the base sizes so that we'll remain closer to the allowable pressure. Then the next important thing is how to select the size of the footings. Size of the footings have been selected so that the extensity of column 1 will be E. Extensity of column 1 will be E. So if the extensity of column 1 is E, if you take moments about this point, then you can say P1 multiplied by S minus R1 multiplied by S minus C is equal to 0. Ignoring the self weight of the strap B. Ignoring the self weight of the strap B. So you can see R1 times S minus C minus P1 times S is equal to 0. And from that you can work out what is the value of R1. R1 is P1S divided by S minus C. Then what we do is we take moments about this point and find what is the value of R2. R2 multiplied by S minus C is equal to P1 multiplied by S minus C, P2 multiplied by S minus C minus P1 multiplied by E. From that equation, we can find the value of R2. So R2 is also can be found. So when you look at R1 and R2, you can see R1 will be bigger than P1. And if you look at R2, R2 will be smaller than P2. Then if you take the equilibrium of the whole system, R1 plus R2 is equal to P1 plus P2. So what we do is, first we select a suitable value for E. We select a suitable value for E. To select the suitable value for E, first we have to find what are the sizes of the base. So what we do is, first we select the approximate size for the base. And the size for the base will depend on the value of P1, that is, the dead load and live load, divided by the allowable bearing capacity of the soil. Then on the basis of that, we can work out a value for the approximate size for the bases. Once we know the approximate size for the bases, we can work out a reasonable value for extensity. For example, let's say, we have got 2 meter by 2 meter for this base. So if the size of the approximate size of this base is about 2 meter by 2 meter, then we know extensity is 0.8 meters. This will be 1 meter. Size of the column is 400, which means extensity will be 0.8 meters. So once you determine the approximate size of the bases, you can work out a reasonable value for E. Once you know a reasonable value for E, we can work out what is R1 and what is R2. We can work out what is R1, what is R2. So the procedure is select a suitable initial width for the foundation considering the vertical loads and the allowable bearing capacity. It is usual to have the same width for both foundations. The inner column will be carrying a higher load than the outer column. Then the selected initial width will give an indication of the size of the outer footing on the base, and on the basis of that, possible to select a value for extensity. Once the extensity is selected, it is possible to determine R1 and R2. So once you know R1 and R2, now you can work out, the length of the outer footing, and the pressure to be taken by the soil. That means you can work out the width of the inner footing. So when you know the width of the inner footing, you can use the same width for the outer footing. And when you know the width of the outer footing and the load on the R2 value, you can work out the length of the outer footing. So that way you can work out the dimensions, and then once you know the sizes of the system, then you have to draw a bending moment diagram and a shear force diagram. As you can see here, you draw the bending moment diagram and the shear force diagram for the system. And when you know the bending moment and shear force diagram for the system, it's possible to determine the reinforcement that you need in the strap beam. So that is the procedure. So because it will take little time, we'll discuss how to design the strap footing next time. And I will stop the lecture here. And if you want to ask any question on this strap footing, you can ask it now. Or any other thing that you want to clarify, you can ask any question now. So these strap footings are quite useful when you have a eccentrically loaded footing, especially on the boundary wall, because you are not supposed to have the foundation on the nearby land. So we have to go for this type of situation. And when you have reasonable soil, you can always effectively use strap footings to ensure that the rotation at this outer footing is minimized.